Section: Introduction. In this section, we introduce our work on large language models, LLMs, which are skilled at producing coherent text but often lack transparency in how they manage semantic information. Previous studies have shown that neural networks tend to represent concepts as linear directions within their hidden layers. Sparse autoencoders, SAEs, can help separate these directions into clear, single-meaning features, particularly in LLMs. However, most existing methods focus on just one layer or the residual stream, leaving the multi-layer aspect of feature development and transformation less understood. We propose a data-free method that uses cosine similarity to align say features across various components, such as multi-layer perceptrons, MLPs, attention mechanisms, and residual connections at each layer. This approach allows us to visualize how features are created, change, or disappear throughout the model, which we refer to as flow graphs. By utilizing pre-trained SAEs that can identify interpretable single-meaning directions, we analyze the cosine similarity of their decoder weights to observe how these directions evolve across layers. This analysis reveals unique patterns of feature emergence and refinement that are not apparent when examining just one layer. Our flow graph construction reveals an evolutionary pathway, akin to a circuit, where MLP and attention modules contribute new features or modify existing ones. We demonstrate that these flow graphs enhance model steering by allowing us to target multiple say features simultaneously, leading to a clearer understanding of the steering results. This framework marks the first instance of multi-layer steering through say features, helping us track the lifespan of these features, comprehend their evolution across layers, and understand how they may form computational circuits, ultimately enabling more precise control over model behavior. To lay the groundwork, we discuss the linear representation hypothesis, which posits that hidden states can be expressed as sparse linear combinations of features within specific subspaces. Each feature's influence is determined by its magnitude, and the number of unique semantic subspaces far exceeds the dimensionality of the model, necessitating an overcomplete basis in the feature space. During processing, the model typically utilizes only a small subset of these subspaces, which are generally one-dimensional but can also take on more complex forms. We also explain how sparse autoencoders, SAEs, are employed to extract these linear directions by breaking down the model's hidden state into a sparse weighted sum of interpretable features. We define a collection of one-dimensional features learned by an say at a specific position in the model. The say is designed to reconstruct the model's hidden states while promoting sparse feature activations. The choice of activation function is critical for achieving the desired representation, with options like jump re-LU and top K allowing us to control the activation thresholds and sparsity levels. Transcoders, which are similar to SAEs, aim to reconstruct different targets and serve as interpretable approximations of MLPs. Section Summary. In this section, we introduce a data-free approach using cosine similarity to analyze how features evolve across multiple layers in large language models, revealing distinct patterns of feature development through flow graphs. We also discuss the role of sparse autoencoders, SAEs, in isolating interpretable features and how this framework enhances our understanding of model behavior and steering capabilities. Section: Features on different layers. In this section, we examine the features from different layers of our model. We note that features from earlier layers are generally low-level, often reflecting basic word characteristics, while those from later layers are more complex and influence the model's behavior. We typically train sparse autoencoders at 3 key points in each layer: the output from the attention mechanism, the output from the multi-layer perceptron, MLP, and the residual stream, which is the primary channel for information flow in a transformer. The MLP and attention modules utilize this stream to process and return data. We find that most features in the residual stream remain stable across layers. To identify similar features between layers, we can create a permutation matrix that maps feature indices from one layer to another, assuming both layers have the same number of features. This matrix helps us understand the relationship between features in different layers. While sparse autoencoders provide interpretable features, they do not clarify how these features interact or how the model processes information. Gaining this understanding is essential for effectively manipulating the model. We believe that linking features across different levels can help us uncover shared characteristics between two sparse autoencoders trained at different positions. This motivates our methods for identifying shared features and designing architectures that maintain consistent feature collections. We also explore various methods for matching features between layers. One method relies on correlations between activations, but it requires a lot of data for accurate computation. We prefer a data-free approach based on the weights of the sparse autoencoders. We find that using cosine similarity between decoder weights is an effective way to measure similarity. To match features, we define a process where we identify the corresponding feature index based on the cosine similarity of the embeddings. We assume that both the feature vector and the decoder weight columns have unit norm. We also introduce a more general matching approach that allows for many-to-one correspondences, extending previous methods. However, we note that our technique is limited to cases where the structures of the hidden states are aligned, and variations in data distribution can also impact our results. Section Summary. In this section, we explore the interconnections among features trained on different layers of sparse autoencoders, SAEs, noting that earlier layers capture low-level characteristics while later layers focus on high-level model behavior. We discuss methods for matching features across layers using cosine similarity of decoder weights, which helps us understand the evolution of semantic structures and computational modes within the model. Section: Tracking the evolution of feature. In this section, we track the evolution of features within a standard transformer layer. We identify four key computational elements: the layer output, the MLP output, the attention output, and the previous layer output. The MLP and attention modules utilize the previous layer output to generate the current layer output. We select a feature from the SAE trained on the current layer output, represented by an embedding in a specific dimensional space. We then compute the similarity between this target feature and the outputs from the MLP, attention, and previous layer by finding the highest cosine similarity among their respective decoder weights. This allows us to understand how the feature connects to earlier layers, with specific thresholds for what we consider high or low similarity varying by layer. We adopt a backward matching approach to answer the question of where a feature originates, as opposed to forward matching, which is less effective for identifying new or altered features. As we move through the model, we notice that the semantics of features change significantly, complicating long-range matching. To tackle this, we perform short-range matching across consecutive layers and create a flow graph that illustrates how a feature's semantic properties develop from the initial to the final layer. While we currently analyze individual features or groups, we see potential for further research into these flow graphs. We also identify linear feature circuits within the model, which are subnetworks that perform specific tasks. Our method helps pinpoint circuits where MLP and attention modules modify features in a mostly linear manner, indicated by high values in our similarity measures. We validate this through experiments that focus on the evolution of a feature's meaning. Flow graphs can guide the model towards desired behaviors by highlighting feature sets we wish to manipulate. By selecting these features carefully, we can maintain alignment with the model's core capabilities, and our method aids in discovering these feature groups. Analyzing flow graphs derived from these features enhances our understanding and prediction of the model's behavior post-manipulation. For our experiments, we primarily use the GEMMA 22B model and the GEMMAscope SAPAC, employing a specific activation function and a defined dictionary size. We also test our approach on LLaMAscope, which underwent a conversion after training. Additionally, we train our own SAEs for the attention output across all layers of the GEMMA model, following the established training pipeline. We utilize Neuronpedia for interpretations and evaluations, although interpretations for newly trained attention features and LLaMAscope were not available. Our experiments are designed to explore how residual features develop, spread, and can be influenced across model layers. Specifically, We aim to determine the origins of features in different components, assess the causal relationships between features, and use these insights to guide the model's output towards or away from certain topics. To identify feature predecessors, we first confirm that the cosine similarity relations align with actual activation correlations. We match a target feature in the residual stream with features from the previous layer, MLP output, or attention output. If none are active, we classify it as from nowhere. We apply this method across various datasets to validate our findings and analyze the distribution of these groups across layers. Next, we investigate the deactivation of features by measuring causal relationships between a target feature and its matched predecessor. We do this by intervening in the hidden state. If removing the activated predecessor deactivates the target feature, we establish a causal link. We test multiple matching strategies and evaluate their effectiveness through a deactivation success rate and an activation change score. Section Summary. In this section, we track the evolution of features through transformer layers by analyzing their relationships and transformations using flow graphs, which reveal how semantic properties change across layers. We also identify linear feature circuits and explore how these insights can be used to steer model behavior by manipulating specific feature sets, while conducting experiments to validate our findings on feature origins and causal relationships. Section: Model Steering. In this section, we investigate how turning matched features on or off across different layers can influence the creation of specific themes. We identify key features related to a chosen topic, apply changes across multiple layers, and assess the quality of the resulting text. Next, we validate our earlier findings by checking when specific features and their predecessors activate together. We categorize each activated feature based on which predecessors are also active. For instance, if both the previous feature and a multi-layer perceptron, MLP, predecessor are active, we label it as from res and MLP. We then analyze the score distributions within these categories. Our results show distinct score distributions among the groups, and we use a statistical test to quantify the differences. We find that two groups can differ significantly if a specific module is active in only one group. For example, the groups from MLP and from MLP and ATT show notable differences in various tests. We observe that from layers 0 to 5, the features from nowhere and from res indicate a chaotic early stage process that stabilizes around layer 5. After layer 18, we notice fewer new features emerging, with most features coming from earlier layers. We also see a three-part division in the distribution of groups, indicating different dynamics at various layers. The datasets show differences in the later layers, with the Python code dataset having the least natural language and tiny stories featuring the most straightforward language. When we deactivate features, we compare the method of selecting the most similar predecessor with randomly choosing from the top 5 candidates. Our findings reveal that the random selection significantly reduces the success of deactivation, confirming that the top choice is crucial for understanding causal relationships. We also find that deactivating a single predecessor has a more substantial impact when it belongs to a group with only one predecessor, suggesting a circuit-like behavior among combined groups. We then explore how changing the rescaling coefficient affects deactivation outcomes. Different groups respond uniquely to rescaling, with positive rescaling being most effective when residual features interact with MLP or attention. Negative rescaling has a more pronounced effect on the from res group, indicating the importance of MLP in these interactions. To test multi-layer interventions, we aim to block certain topics while promoting others. We compare interventions applied at a specific layer versus those applied cumulatively from the start to that layer. We measure the presence of topics and the coherence of the language. Our results show that multi-layer interventions outperform single-layer approaches, reducing sensitivity to hyperparameters. We find that increasing the rescaling value shifts the optimal intervention layer earlier in the model, while smaller values allow the effects to spread across multiple layers. Cumulative interventions generally enhance topic presence but can sometimes lower text quality, For instance, activating features related to religion and God can lead to outputs resembling biblical text, confirming the connections in the flow graph. Section Summary. In this section, we investigate how activating or deactivating features across multiple layers influences the generation of specific themes in text, finding that multi-layer interventions generally outperform single-layer approaches in both deactivation and activation tasks. Our analysis reveals distinct patterns in feature activation across layers, indicating that earlier layers contribute to a high-entropy process that stabilizes over time, while the effectiveness of interventions varies based on the rescaling of features and the nature of the underlying model architecture. Section: Identification of feature predecessors. In this section, we identify feature predecessors. Our findings show that I, the similarity of linear directions, serves as a reliable indicator of activation correlation, and E, the structure of these groups varies across layers, likely reflecting how information is processed in the model. We believe that the groups labeled from MLP, from AT, and from MLP and ATT mainly consist of new features introduced at their respective layers, while groups that mix the residual stream with a module tend to contain processed features. The observed decrease in from MLP and increase in from res groups suggests that later layers create fewer new features compared to intermediate layers. Regarding feature deactivation, we, I, confirm that the top one similarity offers important insights into causal dependencies, and E, conclude that groups react differently when certain predecessors are deactivated, indicating they have unique mechanistic properties and may behave like circuits. The dominance of residual predecessors can be attributed to the residual stream being the primary communication channel. When it comes to model steering, if we aim to reduce a specific feature during evaluation, we usually modify its magnitude. However, significant reductions might require large adjustments, which can disrupt the distribution of hidden states. Since we know which features contribute to the feature we want to reduce, we can also adjust those. This allows us to make several smaller adjustments instead of one large one, helping to maintain the overall distribution of hidden states. We conclude that interventions across multiple layers have a greater impact on the model than single-layer approaches in achieving our goals. Flow graphs can aid in understanding the effects of steering and identifying related features, but the outcomes depend on the specific properties of the graph. We hypothesize that removing topic-related information early enables later layers to recover general linguistic information, aligning with the ability of large language models to self-repair after disrupting the information processing flow through pruning or intervention. Overall, our method offers a clear way to identify and interpret the model's computational graph without needing extra data. This graph can then be used for precise control over the model's internal structure. To our knowledge, we are the first to utilize say features from different layers to steer LLM generation, which we believe opens new avenues for zero-shot steering. In related work, several studies have explored feature circuits in language models. Some have proposed pruning connections between modules that do not impact the output, while others suggested using gradients to determine whether to prune these connections, demonstrating that their method can identify circuits at the feature level. Other research has shown that circuits can be found without a backward pass, relying only on activations and weights. Additionally, some studies have examined feature dynamics in the residual stream during the forward pass, but they focus solely on residual stream features and do not analyze the resulting computational graph or its application to steering. While say features as steering vectors have been explored, those approaches are data-dependent and do not involve multi-layer steering. In contrast, our work builds on these findings by presenting a straightforward, interpretable, and data-free method for multi-layer steering, which also allows us to track concept evolution across layers and identify computational circuits by targeting the weights of pre-trained SAEs.